Hi everyone. We have seen a lot of things till now, and I want to do a quick recap because it's a lot. Even in linear regression, although the equation for the model is very simplistic, but we have been circling around different concepts to make sure that we understand the implications when we try to model our data linearly. So moving on, how do we evaluate this model? And why do we want to evaluate the model so much, right? Why are we fixated on evaluating, interpreting all these coefficients? Because in real life, the data never is perfectly linear. And we have to make sure and we have to gauge with all these techniques whether or not our data makes sense. So there are a bunch of ways with which you can do model evaluation, and that's what we'll look at in this particular section, that what are the different ways in which we can evaluate if our model is a good fit or does it have any problems, and how we can interpret those different problems. So the first one that we'll look at is residual plots. Now, residual plots is something that we have actually looked at in the previous section. And what I mean by residual plots is the different ways in which we can graph out the residuals so that we can see are the residuals uniformly distributed, or is there some particular pattern that the residuals are following, and do we need to change or scale the values so that we don't see that particular skewness in our distribution. So that's one way to kind of gauge how our model is performing. We can draw these plots, and these plots will intuitively give you a sense of the model fit, because graphically you'll have a way to interpret the goodness of the model. Moving on to the second method, which is sum of squares decomposition. Now this one is very interesting. So what we do in this particular method is we define three terms: SST, SSR and SSE. And let me just label it out. So SST is total sum of squares, and then SSR is regression sum of squares, and SSE is errors or the residues errors sum of square. If you look at this name, what does it mean? Total sum of squares. Sum of squares define the mean value of y and then calculate how much the actual values, the observations, are varying from this mean. So this is the variation in y, and you take square of that and take a sum of on all the values. Now that is your total sum of squares. The second term is regression sum of squares. So you have same mean of y, and then what you do is you define all the predicted y values, you calculate these, and then calculate the variation in this predicted value. For all the y values, take a square and then take a sum of those squares. So this is regression sum of squares. And then error sum of square is you take the observation, you take the prediction, calculate the delta between them, take a square and sum it all over. So these are three pretty basic things that you can define. And once you define these things, what this intuitively means is you have a way with which you're saying, okay, this is my total sum of squares. This particular term should somewhat be explained by summation of regression and the summation of errors. Plus there can be some other thing as well. So what I'm essentially saying is I am claiming that SST can be expressed as SSR plus SSE plus some additional term. Okay. Intuitively what this means, let's try to understand what am I claiming here. I'm saying that the total sum of squares, where each actual value of y is differing from the mean, and how much of it is differing from the mean, and I calculate the total sum of deviation, this actual deviation square is explained by regressions deviation and the errors deviation, right? And then this some additional term. Makes sense? Fairly intuitive. Now what I want you guys to prove is you can prove that this some additional term is actually zero. The proof of this goes beyond the scope of this particular lecture, but it is very beautiful because when you expand these squares, so let me just quickly erase this. When you, okay. So what I want you to do is look in this direction, that when you expand these two terms, let's say you open these squares, you will have one term which looks like this, okay, but then you will also have a cross term, right? you will also have a cross term which will be coming from the leftovers that you have, and that cross term is actually 0. Now, mathematically, it goes beyond the scope of this lecture, but intuitively, what that cross term indicates is that the cross term is nothing but the product of this and this. And that cross term, which is the product of this and this, is actually 0 because of the structure of how we are trying to calculate. So one is the error term. So error terms times this particular residue, which is y predicted minus the mean. These two vectors are orthogonal, and that's why it is 0. Now this goes beyond the structure because we are not looking at it from a linear algebra point of view. We are just simply, okay, we had one variable equation, and then from a one dimension equation we were doing all the derivations. But essentially it boils down to the fact that the way we optimized for OLS, ordinary least square, is that the error term is orthogonal to a predicted value. I know it's slightly hard to grasp this idea, but one way you can think about it is that the error terms, the errors, are not at all correlated to the prediction, right? This is the predicted value, at least this part, and this is a constant y bar mean. So the predicted value is not at all correlated with the error, and that's why this dot product or this multiplication, when summed over, is 0, right? So again, if you're a math enthusiast, you should explore this part, that this additional term will become 0. But otherwise, if you just want to understand this intuitively, you can somewhat grasp the idea that there are 2 points. First, the total sum of squares should be explained by the regression part, and then there is the error part, right? And intuitively it makes sense that if I sum these two elements, that should explain my total deviation, the sum of total deviations, right? And then there is another idea, which is the way we optimized to calculate the predicted values of y. That predicted value has no covariance between, so there's no covariance between that predicted value and the error term. So those are the ideas in a nutshell. Now, why are we spending so much time in understanding what is SST, SSR, and SSE, right? The reason is because we can define something like a goodness of a fit with these 3 factors. So let me calculate, or let me define something called as R square. What do I say? Why am I saying this is R square? Because again, I'm just going by terminology because there is a square in these terms. So we'll call this as R square, and we define R square as SSR by SST. So this is a ratio. You can think of SSR by SST as the deviations in data set that are explained with the regression divided by the deviations which exist in the total data set. So what this means, how would you interpret R square? You would interpret this as the goodness, and this will never be greater than 1, right? Because of the nature of it, because of the nature of these equations. So R square, higher the R square, the closer it is to 1, the better your regression captures the total deviation in the data. And that's the idea of R square. So we calculate R square often in our linear fits because we see, okay, I did a linear regression. How well does it capture my data set? If R square is closer to 1, we tend to believe that it does capture a good majority of it. Now, there can be exceptions. There can be cases where R square is high, but again, your fit might not be a good fit, and we'll talk about those cases as well. But essentially what R square indicates is the level with which you have captured, with which the regression has captured the total data set. Now, I mentioned earlier that there can be cases where you have high R squared, but this may not necessarily mean a good fit. Why did I say that? So let's say you have an equation y is equals to beta 0 plus beta 1x. Now this is a one dimension equation, but with just 2 parameters, the intercept and the slope. What if you have more independent variables in this? So you have y is equals to beta 0 plus beta 1 x1 plus beta 2 x2 up to beta m xm, right? In that case, you have introduced more parameters. So each additional parameter that we introduce is actually going to minimize the error a little bit more, right? Because you're giving one more freedom, one more free parameter that you can optimize such that the error is minimum, right? So think about it this way. If you have to think of this intuitively, what we did when we derived the 1D equation, we had these two parameters, beta 0 and beta 1, and we took these partial derivatives to calculate these two, right? Now, if I suppose I introduce one more beta 2 here, one more parameter called beta 2 x2, let's say. If that parameter had no effect whatsoever on the calculation of y, your beta 2, the parameter that you calculate, the variable that you calculate, would be very close to 0, such that the equation tends to or comes back to y is equals to beta 0 plus beta 1x. If that beta 2 had no effect. Now I have the liberty to choose that beta in such a way, I have the liberty to choose this variable in such a way that I can minimize this error. And if I cannot minimize this further compared to beta 0 plus beta 1, automatically with these partial differential equations, beta 2 will become 0 because it has no effect. But if it is not 0, the effect that beta 2 is having is actually going to decrease the SSE compared to what it was when beta 2 did not exist. Now, this is a powerful concept. Intuitively, you can think of it in this way that you have a degree of freedom, you have a free variable that you can tweak to reduce the error. If that variable does not have any effect, the partial differential equations would make sure that that variable automatically goes to 0. But otherwise, whenever that variable does not go to 0 or is comparable to other betas, then you are minimizing the error further. Now, you might ask that I can keep doing that n number of times or m number of times, I can just keep adding more and more parameters, but then you would be overfitting your data. We'll talk about overfitting. Overfitting is you are explaining the data which is given to you with precise nature, but it is so well fitted that it cannot predict the future data. So we have to balance these things out. And that's the key idea that I want you to take, that SSE will go down if you introduce another beta. And that's the reason why high R squared may not necessarily mean that it is a good fit. Because you may have too many unnecessary variables, unnecessary parameters, unnecessary betas, which are making sure that your regression is fitting well and is actually giving you a higher R square, but it does not mean that you have a good fit. It just means you have a overfitted curve. I hope that makes sense. Take a moment to absorb that. So what we do, what's the catch here? Let's adjust this R square. Now again, very, very interesting way to adjust this R square is take a factor. In this case, this factor is n minus 1 divided by n minus p minus 1. So what is this factor? This is an amazing factor. We scale R square such that if the p are the number of parameters, betas that we have in total, n is the number of observation points that we have. In our case, we had a lot of points, and you can see that n would always be greater than p. Otherwise, it doesn't make sense. If I have just 2 points and I'm fitting a line where I have to calculate beta 0 and beta 1, that line will pass through those 2 points for sure. And that's how I can fit the line, right? So you have less parameters, you have more data observations that you have made. We are scaling R square in such a way that we are penalizing every time we increase parameters. So if we keep increasing the number of betas, we are bringing R square down by adjusting it with this factor. Now, why this factor? This factor because this represents the degrees of freedom in both SSR and SST. SSR is the regression, and the regression has degrees of freedom as n minus p minus 1, and SST is the total which has the degrees of n minus 1. I will explain why SST has n minus 1 degrees of freedom because it's very interesting, and then reason it in a similar way why SSR has n minus p minus 1 degrees of freedom. And let's also touch on what degrees of freedom essentially mean. So let's take SST. SST is the degrees of freedom in total data. How did we define SST? Let's go back to that particular equation. So we have SST as this one. Let me quickly erase a few things here and there. Okay. So I have SST as this. What is, if I have to take a mean of this particular total sum of squares, should I divide by n or should I divide by n minus 1, right? Think about it for a moment. If I have to take a mean of this one, I took the summation from 1 to n. It makes sense to divide by n intuitively speaking because I did n summations of this. But I will divide by n minus 1. Why is that? And that's a beautiful concept that I can illustrate by emphasizing one point that we have not touched upon, which is what is the mean. So we define mean, which is y bar, as sum of all y values divided by total number of values, which is n, right? That's how you calculate the mean. So let's take an example. You have 5 values of y and then you calculated this y bar, which is the mean in this case. Suppose in the next case, suppose what you had was, you had 5 values of y, 1, 2, 3, 4, 5. You calculated the mean from these numbers, which is 3 in this case. But let's say you lost track of values and you could only recover that you had 4 values in your data set, 1, 2, 3 and 4. And you knew that the mean was 3. So with the knowledge of mean, you can precisely point out what the 5th value was, right? With the knowledge of n minus 1 values and the knowledge of mean, you could precisely point out that the 5th value has to be this one. Now, is it making sense? So the intuition here is, if you calculate mean, you are taking 1 degree of freedom away. What I mean by that is, if you have mean and n minus 1 values, the nth value is now fixed. It cannot vary. We have absorbed some variation already by taking this mean and using that mean value to calculate the rest of the numerator, right? So intuitively, what I can see is, now because I am calculating this deviation, I will only divide by n minus 1 because that's all the degrees of freedoms that are left with the data set. Because what I want to do is, I don't want to be in a position where I divide by a larger number, which is n, and I underestimate the total error or the total deviation, right? I don't want to underestimate my total deviation by dividing by a larger number. And this is the intuition behind why we are dividing by n minus 1. And similarly, if you think about SSR, which is the regression, now we had the mean absorbed 1 degree of freedom. And when you are calculating these parameters, suppose this had p betas, beta 0 up to beta p minus 1. So we had p parameters. So we will divide by n minus p minus 1. And that's the intuition, because I don't want to be in a position where I underestimate how much is the deviation that's coming from regression or how much is the deviation that's coming from the total, right? So that's the intuition why we use this particular factor to scale R square in a way such that every time you increase the number of parameters, you are bringing down the R square, you're adjusting the R square to accommodate for the fact that you have increased the number of parameters. Now, moving on to the next thing that we analyze, which is mean squared error and root mean squared error. Mean square error is nothing but SSE divided by n minus p minus 1. Since we defined something called mean squared error, so we'll just divide it by n minus p minus 1. Now we looked at the intuition around why we are dividing by n minus p minus 1 instead of n, because those are the degrees of freedom that are left. And we had the total deviation, total error. So remember, SSE is the component which is not explained by regression, right? So you want to take that particular component which is not explained by regression, which is like the actual minus predicted, right? You take the sum of all of those squares and you divide it by n minus p minus 1 to get a mean square. Root mean square is just the under root of that. Why are we taking under root? Because we want to get to a place where we can compare the error to the unit of y. Now, because these are y squared units, you cannot directly compare the squared units to the actual data set, right? And that's why we take a square root of mean square error to calculate and to actually have the same unit as your observed value, so you can compare those two. And that's about mean square and root mean square. Now, moving on to the final thing that I want to touch about model evaluation. I know model evaluation has gone into a little more depth than I had expected, but training versus testing error. We can calculate all these different things on a training data set. So that's what we have been doing, right? If you think about it, we had all these points available, and then we drew this best curve, best fit line, and then we tried to calculate all these errors. But let's say we have, after we drew this line, we have 10 more data points that came up. And this is my test data points. I want to calculate, does this line actually predict the right values for these test data set? So let me give you a brief overview or brief summarization of what training versus testing mean. When we have a large data set, we can divide it into two chunks. One is the data on which we train the model, and then we keep one chunk of data aside for which we have the actual value of x and the actual value of y. We keep that aside so that we can check if the model that we used is giving good predictions for that testing data set, is giving good predictions on that leftover data set that we did not use to train. And this is a good mechanism to just kind of check how your model is performing, right? So we divide our data set into two buckets, training and testing, and that's what we mean. We can evaluate all these error metrics and all these variables that we calculated, r square, root mean square, all of these things on training as well as testing data set. So one example, one small exercise. Let's say your model has a low training root mean square error, but a high testing root mean square error. What does this mean? So this simply means that your model has a problem of overfitting. Your model performs really well on the data that it has already seen, but it is not able to perform well on unknown data. And that's what we also touched upon when we were saying R square is high, but it does not necessarily mean that the model performs well. So overfitting is a big problem, and it is always good to test all these errors, all these error evaluations on your testing data as well as your training data to evaluate how your model compares when it sees new data versus what it does when you have a set of data it has already trained on. So with all the things that we have done in linear regression, I feel like we have not done a lot of linear regression mathematically. Like the equation for linear regression is pretty basic and pretty simple. But what we have spent a lot of time on is to understand the nuances in which linear regression is a good fit and where and in which cases this might fail. And that's all. I think that's all you have in linear regression. Thank you so much for watching till the end.